Start recording. There we go. Hello everyone and welcome to Handmade Hero, the show where we code a complete game live, from scratch, no libraries, no engines, all by our very lonesomes, just me and the fine fellows on the stream. I don't actually know how many people we've got tonight, but there's always a good crowd here, and they're always very supportive, and it seems like they're really some pretty awesome people from interacting with them on the forums and stuff, so I really couldn't ask for a better team to put this game together with. I can tell you that right now. Now, one of the things a lot of people ask is, why are we coding a game from scratch? Well, half for education, half for fun. I think there's a lot to be learned from doing an entire game from scratch and not relying on other people's code, because it forces us to learn everything, and we get to know basically everything that goes on inside a real professional quality, performant game engine. But also because it's just a lot of fun. It's fun to go, spend some time doing things just because they're interesting, and so sometimes it doesn't necessarily have to be the most rational choice. Maybe you could go get a library to do something, but sometimes just once in a while, and this project is that once in a while, certainly for me and for a lot of other people, to kind of get in there and just say, hey, let's play around with this for a while. Let's see what we can do with it. And frankly, I think that's a lot of fun. It also tends to be where a lot of new stuff is determined. Like maybe you go in somewhere thinking you're just doing something for fun, and it turns out you come up with a whole new way of doing things that's better than what's currently being done out there. So that's pretty cool too. So anyway, here we are on day 41, which is basically we do roughly an hour a night of programming here on the stream. And so 40 hours is one work week. So basically we are at the point where we have finished one work week's worth of work. And we have our game running. It's got a little guy who walks around inside of a tile map. Basically what we wanted to do was start moving from that into something that's more of a full game, that's got like a good character motion feel to it, something that's got some nice graphics for the backgrounds and that sort of stuff. And what I decided was we were right at the cusp where I had to start talking about math for real, because basically everything that we want to do from here on in is going to involve math that's more complicated than just basic algebra. Pretty much everything on the stream that we've done so far has been stuff that you could understand with very basic algebra skills. And so now we're kind of crossing that threshold where that's not going to be true anymore. So I thought like it might be a good idea for those people out there who aren't super comfortable with a lot of different math stuff to just kind of start giving a little bit of an overview of that, and maybe spend a day or two talking about math and getting people on the same page. And then from then on, we can kind of point it out as it comes up. So I do apologize for people out there who already know math, especially those people out there who already know math better than I do, because obviously you're going to be pretty bored through some of this stuff, and that's fine. That's just, what can I say? We got to go over it at some point, so I do apologize for that. But hopefully, at the very least, it'll still be interesting stuff to talk about, and maybe you can also help out other people on the stream who are having trouble, who are new to the math and don't necessarily know all this stuff already. Okay. What I did, because I thought this would be interesting to start us off for our Monday stream, what I did was I decided that I'd like to sort of make this next hour here sort of be a general answer, in so much as can be as one can be made, to the folks who often ask the question, and a lot of times these are perhaps younger people who ask this question, people in high school or whatever, who are maybe interested in game development but don't know very much about how math and game development relate to each other, who ask the question like, do I need to know mathematics in order to be a game programmer, or how much mathematics or what mathematics do I need to know, how important is it, that sort of thing. And I hear that question asked a lot, and I've never really stopped to put together a real complete answer. Usually just what I say is it depends on what kind of programming you want to do. If you want to be somebody who programs just straight like very logic oriented code that doesn't really do a lot of motion stuff, that doesn't do a lot of randomness and stuff like this, then maybe you could be a game programmer, like a light game programmer, without really knowing very much math. And certainly if you want to do programming in other disciplines that aren't game related, there are entire like disciplines of programming that really don't involve any math at all. Like you could probably have a career that's very well paid doing stuff that had nothing to do with math most of the time in other areas of programming. But the reality is that if game engine programming, like if actual real game engine programming is something that you are sort of looking at, like you want to be able to be either a full spectrum programmer or somebody who does game engine work, the truth is that math is actually used pretty much in everything you do. So it's almost impossible to escape having at least you know, a pretty good grasp on a number of mathematical topics. It doesn't necessarily mean that you have to be a really good mathematician. I know I certainly am not, but it does mean that you have to have that familiarity and you have to have a certain facility with these math concepts in the sense that you use them like tools and you have to be very fast at using them like tools to get work done. And that is just really the reality of math. And so what I wanted to do today was I tried to make a list, and I'm sure it's probably an incomplete list, but I tried to make a list that was all of the types of mathematics that just me, just myself, just I have had to use in making game code over the past 30 years. So basically this is, and what I'm going to do today is basically go through this list and show you why each one was necessary and what I actually used it for, in so much as I can give sort of a capsule summary. And I think that'll basically be the best way that I could set us up for our discussions about math that will go on for the next year or two as we come to the various things that we need. I'll be able to kind of refer back and go, remember I talked about this? Well, now's the time that we have to start using it. And so I'd like to just kind of go through these and see if I can basically give that sort of high-level conceptual overview so that people who really just don't have a lot of math background here will sort of now know, okay, like, here's actually sort of the breadth of the stuff that's actually involved in just one programmer's stuff that they've done over the course of their career. And it's also safe to assume that if you picked another game programmer, you'd get a different set. A lot of it would probably intersect with mine, but they'd probably have some stuff on there that I don't have. So they'd probably know some branches of math and some things in various branches of math that I never had to do and don't know, and vice versa, right? Okay, let's get started with the basics. Okay, so I believe let's see if we're back to our little hand in Krita. I don't know why Krita loves the little hand so much, but it really does seem to. All right, I'm going to go ahead and move my, my thing here for drawing. I'm actually using the drawing tablet today. Drawing, yeah. My handwriting is not so good on tablets. I apologize for that, but that's just how it goes sometimes. All right, so let's start by pointing out just the most basic thing, which is that if you are in high school, I'm assuming that you probably have done arithmetic, right? Algebra, just basic algebra, you know, basic algebra, geometry, trigonometry, geometry, there we go. I don't know what's up with this pen right here. And calculus, probably. Now I realize that some people maybe haven't actually taken calculus in their high school years, but I think most places probably it would look something like this. So you'd have arithmetic, algebra, geometry, trigonometry, and calculus. You've had this by the time you would be in high school sometime. Maybe you'd have to get to very senior year to do calculus. Maybe you'd do it earlier. I'm not sure, but it'd look something like this. So obviously, you know that these two are involved in all kinds of programming because you've already seen me do these on the stream. Okay, so two things that you learn in grade school, you've already seen me do on the stream. Arithmetic is, we basically have to know that because that's what we're programming the computer to do all the time. Addition, subtraction, multiplication, blah, blah, blah. You've seen me do a ton of that on the stream. Obviously, the computer's doing tons of it. Per frame, there's no question there. Algebra, same thing. You've seen me use it lightly so far on the stream. I believe we had to solve for something once. You saw me rearrange terms just the other day when I wrote down something of the form. I believe I did A plus B minus A, right? And I said, I could go ahead and rearrange this. I crossed out the A terms or something like that. And then I also did one for the T. I distributed the terms, so I used the distributive property for T. I don't know if you guys were watching when I did that, but that was something I did the other day. So you've already seen me do light algebra on the stream, and it will only get more of that as we go. So you've already seen me do these. What you haven't really seen me do is these, but they are certainly there. And so I'll briefly say how we're going to use those and how I have used those, and then we'll move on to the more serious mathematics. Okay, so basic geometry, and by that we really mean Euclidean geometry. So basically the kind of geometry that you typically learn in high school is called Euclidean geometry. And generally, I don't really know why Euclid gets his name on it. Maybe he invented it. I don't know. I'm not a mathematician, like I said, so my math history and my actual math knowledge are almost nil. So everything that you want to know specifically, you will always have to check. I can only tell you about how I program games with math. That's the only thing that you can guarantee. So basically, yes. I just assume it's named after Euclid. I have no idea. But Euclidean geometry is basically the study of geometry in the types of spaces that we typically care about in games as a general rule, which is to say systems where we have coordinates and those coordinates meet at right angles to each other, right? So basically, we've got these coordinate systems where we have an x-axis and a y-axis, and the y-axis, it is generally considered orthogonal. It is something that generally doesn't interfere with the x-axis at all. So when we pick a point, right, we don't have some weird coordinate system where the y-axis is like a bendy curve or something like this. It's always this nice straight thing, x and y, and if we have a z, same thing happens. We've got this nice orthogonal coordinate system. That's what we tend to work with in games. We tend to give points in space coordinates using either xy pairs or xyz tuples, right? Triplets, I guess you might say, right? And Euclidean geometry is basically geometry that's sort of the one that comes into play when you're working on these kinds of systems. Whenever you've got these right-angled coordinate systems, that's a textbook case for Euclidean geometry. And Euclidean geometry allows us to start doing, it's sort of what we are talking about when we are thinking in these terms, right? And so you've done these sorts of things. I mean, I'm trying to think about what the sort of stuff is that you do. I can't remember back to in high school when I started doing these. Like, it's like the trigonometry and the geometry kind of blur together in my head. I don't remember if things like proving the congruence of triangles, like for example, if I had, a triangle here or something like this, and then I had another triangle here, right? Like, let's say I have these two triangles. Proving that these two triangles were basically congruent because they had angles in common, these sorts of things. I think that was the kind of stuff that they did in high school geometry. I'm not sure. But point being, even that simple congruence of triangles, that is like the cornerstone of three-dimensional projection, for example. So when you do three-dimensional rendering, and we will do some of that, a limited amount, even though this is a 2D game, even just that basic stuff that you learned in high school is actually all totally applicable already in games. Congruent triangles happen all the time. So yeah, trust me, even though it seems kind of straightforward and simple, even the geometry that you learned in high school is the kind of stuff that you will end up using. Now, trigonometry is used all the time, a ton. Basically, the most common case of it in games is the really simple case of when you need to translate between things that happen in your coordinate system. Again, you've got like an xy coordinate system here, and you have very typical cases of trig where you've got stuff like you have a point out here somewhere and you want to know its angle of deflection, basically off of some other point, for example. Maybe I've got 2 points, like a point here and a point here, and I want to know the angle between them. A lot of times you'll do this for game programming. You want to be able to rotate things to point at other things, or you want to be able to do stuff like figure out the rate of turning of some things that you want them to have, all these sorts of things. Trigonometry, going back and forth between some angle theta and some real sort of notion of what that means in terms of a direction in space or in terms of locations of points in space. Again, the most basic stuff that you learned in trigonometry, already useful in games, and it only goes up from there. So just write stuff that you already learned in high school, we will be using on the stream repeatedly. And so that's a real big one. And it really never gets old. Like, no matter how complex the thing I've ever written, trigonometry always pops up, just like algebra and arithmetic. It's baked into everything because games at a fundamental level are very spatial, right? They're just very spatial things. And so calculus is kind of the one that maybe doesn't rear its head so often in games, depending on how you choose to implement them. And the reason I say that is because you can cheat out of a lot of calculus. You can sort of be Mr. chooses not to do your calculus homework, if you're a game programmer, by using things like fixed frame rates and other stuff like this. And when I say fixed frame rates, I don't mean like the kind we're doing where we're saying we're trying to keep our frame rate constant. So if it's 30, we're trying to stay at 30. If it's 60, we're going to try to stay at 60, and so on. I mean more like you literally only have one type of time step you can take. You can only go forward at a 60th of a second, and you have to run everything at that. And the reason is you can just sort of bake constants into your motion equations that just sort of work, and you don't have to think about the integration of things over time, which tends to be, and the derivatives of things over time as much, because you can basically fudge your constants and just kind of like tune things to work sort of without necessarily having to involve yourself in a lot of this. So sometimes, depending on the game and depending on how you choose to program it, you may be able to get out of doing some of this. But if you don't do that and you would like to be able to support, you basically be able to write code that can dynamically have its, that basically doesn't have to be rewritten if you want to change what the time step is and you want it to play identically or nearly identically in terms of what motion things take, then calculus starts to come into play big time. And the reason for that is because, again, when you're talking about t, when you're talking about time, and you're talking about the arrow of time, so basically you're talking about time steps where you've got some kind of a delta t. You've got a difference in time between one game state. This is the game state that we were at before, and we want to advance to a new game state, right? Then basically what you're talking about is you're talking about taking a bunch of things that are specified in terms of instantaneous acceleration or velocity, meaning, let's say, for example, 9.8 meters per second squared, I believe, is the typical constant for gravity where we are in the world. And if you think about how these sorts of things are specified, that is how gravity actually works. That's the rate at which gravity accelerates objects. And so if you want to be able to use gravity properly, you would specify it either as 9.8 meters per second squared in your game, or you would have some own made-up value that you made up for what you wanted gravity to be. But in order for it to actually act like gravity, you then need to do integrations of this acceleration, which is actually the second derivative of position, stuff we'll be getting to later, right? You need to be able to integrate this up into the velocities of objects so that you know how fast they are going, and then finally up into the positions of things so that you know where they are on the screen. And again, integration and derivatives, which are basically the things that step you up from acceleration to velocity position, that's integration going upwards. Derivatives are what take you down from position to velocity to acceleration. That is all, calculus's bread and butter. And so certainly, even if you were doing a variable time step game, even the most basic stuff, again, that you learned in high school, which you probably learned this, this basic stuff, and if you were in physics, you actually literally learned this, not just integration and derivatives. You learned position, velocity, and acceleration as well. Even that most basic stuff comes into play on every frame of a game because everything in the world tends to have, even in very non-realistic games, tends to want to have very consistently behaving physical properties that work the way they do in the real world, just perhaps with different constants. So things, maybe have more friction on them, or they are gravity stronger or less strong, that sort of stuff. But you still want to obey sort of those general ways in which things work. Okay. So that's the basic stuff you learned in high school, and all of it is actually useful in games. It really does come up in a lot of different places, and I'm only just mentioning a few of the ways. There are lots more, right, for each of them. Now, I want to point out something just to give one simple example, which is complex numbers, right? You may have seen complex numbers in your high school classes, right? Normally a number, we think of a real number, it's like 3.52 or something like this, that's our number. And we just think of those numbers as what we normally compute with. But if you remember from your grade school math and so on, they also introduce things like complex numbers, where they will tell you like the square root of -1 equals I, and they will start to write things that look like that, right? And there are these numbers that have two parts. They have a real part and what they call an imaginary part, right? And, probably, I don't know if you were anything like me. Like I said, I don't have a natural aptitude for math. And so if you were like me, you probably looked at that and went, well, I'm pretty sure I'm never going to use that again because I don't even have any idea why anyone would ever care about this, right? It seems completely ridiculous. Turns out not to be true. In fact, even just basic stuff you may need to do with 3D graphics will involve numbers that are not only similar to this sort of thing, but are actually even more complicated than it. And I will touch on those in a second. But basically what I just wanted to do is kind of have just sort of a quick mention of the fact that even the things you probably thought were not interesting or will never be important in some of these subjects actually end up being important. Because most of the stuff that you learn in high school math is actually pretty practically applicable to games. All right, so more on that in a second. So now let's get into the stuff that you probably didn't have much of in high school. I don't know, maybe your high schools were more rigorous than mine, or if you went to a private high school, I went to public high school. Private high schools might be fancier. I don't really know. And so you may have had more mathing, right? But now we're just going to go through stuff I learned after I got out of high school while working on games to work on games. So this is only stuff that was used in game technology, right? This is none of the stuff that I'm about to say is stuff that I did strictly because I was curious or was interested in math. These are literally all things that I had to learn because I actually needed to type some code into a computer, right? Period. All right. So first of all, linear algebra is one of the biggest ones that everyone talks about, and it's true that it is very important, and it tends to underpin a ton of things. So linear algebra, the most obvious place that people face it is basically with vectors and matrices, right? So you've got vectors and matrices, which you've probably seen even if you don't have any idea what they are or why they are. You've probably seen them even in just 3D editing packages. Vectors are, of course, those what we use to represent our points in space, like those tuples, like the x, y, and z, or even RGB in color space, right? Vectors are basically one-dimensional groupings of, well, I shouldn't say one-dimensional. They are a matrix is a 2x2 thing, right? It's got numbers in it in sort of I don't know how else to say it's other than 2x2. It's got rows and it's got columns. Let's put it that way. A vector is not that way. A vector only has one dimension to itself, but the vector itself is said to be in some number of dimensions based on how many it has, right? It's always one of a row or one of a column, right? So it might be XYZ written that way, or it might be XYZ and RGB written in this way, which is actually a little more common due to some various stuff that we'll get into later on in future episodes. So it only has one row or one column, but it has as many elements as it wants in it. So a vector might have, like, typically we'll deal with 3-dimensional vectors, 2-dimensional vectors, or 4-dimensional vectors are very common. X, Y, Z, W, and RGBA, for example, are typical examples of 4-dimensional extensions of these 3-dimensional vectors. And basically what they are is, like I said before, they represent points in space or anything else that we might want to talk about when we have things that are interrelated in some way. Like these are all properties of a single point, let's say, in space, and we want to bundle those together. Now, matrices are very similar. In fact, vectors are kind of just a special case of a matrix, if you will. They are something that only has one of their dimensions filled, and it doesn't actually have, they're not n by m, they're just n wide. And so, something that had more of those, like I drew before, F, G, H, I, something that has more of those, and it doesn't have to be 2-dimensional, it could be 3-dimensional, it could be as many dimensions as you want, and then it also has, each of those dimensions has a certain width, so they might be 3x3 matrices, 2x2 matrices, 4x4 matrices. So typically what you will see the first time that you'll encounter stuff like this is, again, points in space or colors, very common, and then transforms on them. Because what you will typically see is you will typically see transforms of vectors written as vector matrix math. And the way vector matrix math works is you'll typically see it written like this. You'll basically see it done in a fashion that sort of does this drawing, right? And the way that it works is vector matrix multiplication, for example, in this case, is when you take each element of a vector and multiply it by each element of a matrix in the order rows of the vector times columns of the matrix to fill in one here, and then again you do the same pairing here, so I'd have AX, BY, CZ, and I can actually write one of those out for you. This is not something that I want to cover right now, but just to give you an example, AX plus BY plus CZ, right? So you basically do each term X times A, you add Y plus times B, and you add Z times C, so you basically are doing that multiplication. You then move down to the next row and do the exact same thing again. So here you'd get D times X plus E times Y plus Z times, F times Z, trying to keep consistent order there, and GX plus HY plus IZ, right? And so typically, you'll see a lot of this. And the reason that these are used is because these matrices can encapsulate in this format any kind of way that you could transform a point such that it still maintains certain criteria, most of which are okay, like most of which we don't mind always preserving. So by encapsulating the math in this way, you can do scale, you can do shears, you can do movement, like translation, right? You can do a number of things that you might want to do to your vectors. And what's more is matrices themselves can be composed. So basically, if I have a matrix that represents a scale and a matrix that represents a shear, I can multiply the matrices together and get a scale shear matrix, right? So this ends up just being a very efficient way to do some of these 3D graphics things. So that's typically where you will start to see linear algebra first. Now again, not going to explain any of that today because today is just the overview day, but we will talk about it certainly later. But in addition to those things, those are actually very basic things that you might use linear algebra for. But linear algebra is actually a lot more powerful than that because linear algebra actually at its heart is more about solving simultaneous equations. And I don't know if you've ever seen any of this before. If you've only had high school math, you may not have ever gotten to this. But you certainly have done the simultaneous equations part. You may just not have it, seen it phrased in the term linear algebra, or in the ways in which linear algebra often tackles it. You will have seen something certainly in your high school math, something that looks like this, where you have 5x plus 3y equals 0, and let's say 2x plus 2y equals 0, right? You will have been given these equations, and you will have been asked to solve for x and y. And what you will have been told, right, is you will have been told something along the lines of, as long as you have as many equations as you have variables, then you will be able to solve the system, because you just solve one equation for the variable, and then you substitute that back into the other equation, solve that, and then you've got the answer, right? Well, linear algebra is basically the formalization of that process. Basically what you end up doing is you will take all of your equations that you have and you will pack them into giant matrices. So each row will basically be an equation, typically, this sort of thing. So basically, if I was doing that one again, where I had my 5x plus 3y, the 5 would go there and the 3 would go there. It would only, well, let me draw the 2 by 2 matrix of that actual thing that I just wrote. It would be something like this, 5, 3, 2, 2, like so. You would write this matrix, and then you would say that basically I've got a vector that's multiplying by that x and y, right? And that, what I want to do is I want to solve that. Again, maybe it's 0, 0 like we had written before, or maybe there's some actual values in here, whatever. Linear algebra is about systemically being able to solve these vector matrix equations. And basically there are processes that you can run, either iterative or direct, that will basically solve entire systems for you without making you go through and have to do all the finicky, solve for one variable, back substitute the other one, and blah, blah, blah. So basically you can scale this up to things where you solve very large systems of equations that can be huge, right? Now, the other thing that's interesting about that is you can actually solve equations. Solve is the wrong word, but you can actually come up with answers to equations that you actually couldn't not possibly have solved in the regular way that you would do mathematics. For example, you might have things where you have equations and variables that you don't have enough equations for, like something like this, where I've got 2 equations but 3 unknowns. You can actually do things as well that allow you to do approximated solves, or things that allow you to get answers for things that simplify down to show you the space of the possible solutions. If you have like more than one, if you have one or more variables that cannot be exactly solved for, they can give you basically what the shape is of all the solutions, like what it looks like and spatially and so on. So there's just a lot of very powerful things that you can do with linear algebra that aren't just about manipulating vectors to matrices. And so there's just a huge amount of stuff that's involved there. And of course, it's all very applicable to computer science, because really a lot of it was sort of designed to make mechanical sort of the manual processes of algebra. So a lot of it's very intimately related to computer science as well. So anyway, that's linear algebra. Now, once you start working with multiple things, like, like I said, you've got X, Y, Z all over the place. And we've got all these points, and typically everything in a game has at least an XY coordinate, if not an XYZ coordinate, and we're trying to do all these things, in sort of these multidimensional spaces. Typically, regular calculus, the kind that you learn in high school where you just have just basic calculus, typically isn't going to cut it. And what you need to start doing at that point is partial differential equations, right? Which is a form of calculus equations, or PDEs, if you will. Partial differential equations. And what partial differential equations are is they're basically like what you were doing in high school calculus, only instead of only doing it with one variable that can change, like in other words, normally in high school calculus, I believe, and I don't know, maybe your calculus class may have been better than mine, but in my calculus class, for example, we'd have t, for example, would be a variable that can change over time. But then if there are any other variables in the systems of equations, they were assumed not to change over time, or these other sorts of things, right? Well, partial differential equations is basically the sort of study of how you work with things where you have lots of variables that could be changing, and you need to be able to work with them. And so what partial differential equations is basically about, it's basically about applying that high school calculus where you were able to do derivatives and integrals and stuff like this, to systems where everything could be changing. So you maybe have an x, a y, and a z, and all the x, y, and z are all things that might change, right? So in that case, what you need to do is you need to take derivatives of your functions with respect to x, y, and z, and then you need to be able to work with them, sort of to, I'm trying to think of how to say this in the best way, in order to sort of do the sorts of operations that you could do if you only had one variable when you have multiple variables. And so a typical example of this, and like one that I used, for example, in the past, is if you have something like a function that's defined in all of space. So for example, a lot of times you'll see something where you define in games, you will define some function that is spatial. So for any point in the world, you have a function that comes back and tells you what the variable, what the value of this thing is in the world at that point. And this could be used for any sorts of things, and this function could be anything, who knows what it is, something we made up. But one example would be, let's say that we're doing some procedural world generation, and we basically say that for any point in the world, we want to know how foggy it is there, or something, right? So this f is just literally the fog density at that point, right? Then typically something that you might want to do is say for any point in the world, and you know what, maybe an even better one would be, if I could simplify it slightly to something that's maybe a little more relatable than fogginess. Let's say we have an fx of y, and it gives us back the height, right, of like a height map. So it's some procedurally generated terrain, right? And what I want to know is I want to know at any point, since I have this function that gives me back the height, I want to know what the sort of the slope is at that point. Like what direction points up the steepest ascent of the place that I'm at on this, whatever this height generation function is. Well, that's a textbook case of partial differential equations. Basically, there's a thing called the gradient, which is when you take the partial derivative of a function with respect to each of its dependent variables, and you slam them into a vector. So you'd have the partial of fx and y with respect to x, and the partial of f of xy with respect to y, and that would basically give you that vector that you wanted, which is to say the direction in which the height is changing. So that's just an example of something that you might do with it. It's probably a pretty weak example. And to tell you the truth, my partial differential equation foo is really weak. If I had to pick one thing to be better at, it would probably be this right here, because it comes up a lot in physics, and I've just never been that great with them. I just haven't had enough experience with them of really working with them to ever become that good at them. So it's unfortunate, but I'm lousy at these guys. I remember the gradient pretty well because I did a bunch of work with gradients at one point, but I was doing some implicit surface rasterization stuff, and yeah. Anyway, closely on its heels is ordinary differential equations, which, despite the fact that they sound like things that only a pure mathematician would love, they are actually things that you do find surprisingly common in game programming if you actually want to do it right. So what an ordinary differential equation is it's seemingly a solution to what appears to be, or I should say it appears to be a solution to something that sounds unsolvable when you state it first, but it turns out it actually does work in practice. Thank you to the brilliant mathematicians who figured this stuff out. But basically, when you have things like, basic calculus sorts of stuff that you might want to do, like position. I mentioned this just a moment ago. Position, velocity, and acceleration, right? If you remember from either high school physics or high school calculus class, then basically what you have here is these functions are derivatives of each other. So a position is where something is in space. Its first derivative is velocity, which is how fast things are moving, and its second derivative, again, all high school calculus terms, its second derivative is acceleration, okay? So if I have a function, right, function of t, which is my position, then I know its first derivative, which is usually written like that, is the velocity, and its second derivative is its acceleration. Now, I will end up, once I start trying to work with these things, I'll end up in a very unsavory circumstance once I want to do something with, for example, drag. Now, drag is, for, you've all heard of it with respect to airplanes and cars, certainly. If I have something like a car, and I'm making a racing game, wow, that's an awful car. Let's try that again. Let's say I have some kind of futuristic looking car here, something more like this, right? There we go. Oh man, this car is looking good, dude. Look at that, look at it go. Look at its majesty. Then certainly we're all aware of the fact that as air comes and it hits the surface of this car, it actually imparts some force to the car, and that force pushes the car backwards in some sense. So despite the fact that the car is trying to accelerate, it also has to contend with the fact that it's getting somewhat decelerated in the direction it wants to go by the force, the air resistance or drag that's on the car. And in fact, they do a lot of work with aerodynamics to try and make cars as aerodynamic as possible to kind of deflect air in a graceful fashion so it doesn't impart as much force onto the car as it otherwise would, right? Well, if you start to have drag, the first thing that you'll learn in physics when you start to talk about drag is that it's proportional to the surface area of the thing getting hit by the air and the velocity of that air, right? How fast is the air going? Well, the velocity, right, is in this space. The velocity is in the first derivative of position. But the computation for drag is actually an acceleration. Drag is an acceleration which operates down here, right? So that means that the force that you're trying to, well, I shouldn't say acceleration, it's a force really, that, force and acceleration you can transfer by using F equals ma, if you remember that from physics class, but you don't need to know that now, don't worry about it. Anyway, velocity, if I'm going to try and compute it, well, the velocity is the thing that tells me how much force I have on my drag. That's what tells me my drag force, right? But if velocity tells me my drag force, and drag force is what I need to integrate up to get my velocity in the first place, I've got this nasty cycle of this, the actual thing I'm trying to compute defines the quantity that I need to use to compute it. So it's like you can't possibly solve this equation. It's like something that depends on its own derivative, right? And you're just like, I don't know what to do here. I guess I just have to fudge it. Not true. That is what ordinary differential equations are. Ordinary differential equations is essentially the study of equations that are their own derivatives or integrals, however you want to look at it. And basically, these sorts of equations can actually be solved exactly for ordinary differential equations if you want to a lot of the times. So you can actually make this work out precisely if you really want to. And similarly, another very typical one that's kind of fun that people don't think about very often, but that's totally true. Another place you'll see ordinary differential equations pop up is if you want to make zooming be proportional on distance from an object. So for example, let's say I've got an object and I've got a camera. Here is my camera. This is my little, well, you know what? It's an eyeball, my little eye that's looking at this thing, right? Here's my little sphere that I'm looking at. Well, a lot of times you might want to put zooming on the mouse wheel, right? And so basically what you want to do is as you roll the mouse wheel forwards or something, you get closer, and as you roll the mouse wheel backwards, you get further away. Now, when people implement this poorly, and by the way, I'm looking at you, a lot of 3D software vendors out there, because a lot of people implement this incredibly poorly, what they will do is they will, for when you roll the mouse wheel or do whatever you're going to do, they will actually move you a constant amount for each click, or as you sort of drag forwards or whatever. They'll actually move you a constant amount closer to the thing. And that's awful because since zooming, when you get closer to something, the amount that it gets bigger in your field of view is not the same depending on where you are from it. If you're right next to an object and you step 1 foot forward closer to it, it becomes huge in your field of view, whereas if you were 50 feet away from it and you took 1 step forward, its size would barely change at all. So the concept that the user would ever want to step a constant distance is ludicrous, right? What they actually want to do is they want to step an ever diminishing distance closer to it. So they want to basically start out with large steps getting closer, and then they want to get smaller and smaller and smaller and smaller. So what does this mean? Well, it means that the distance that you'd want to move is proportional to the distance itself. So basically, the derivative of the distance is proportional to the distance, right? Classic ordinary differential equation. If we want to do a smooth zoom in on an object that zooms smoothly over time, right, animated, so forget mouse wheel now, we're trying to animate in on that object, and I want it to be a perfectly smooth zoom that operates at a variable frame rate, I've got to solve an ordinary differential equation, because in order to do that, I have to say that I always want, during the whole time step, no matter what the time that comes in, I want to solve that equation to figure out what is the distance that, if I was moving continuously, would always continuously give me a movement distance that's proportional to the actual distance that I am, right? Again, ordinary differential equations, it's actually a very simple problem in ordinary differential equations. Sounds incredibly difficult if you don't know them, but once you know them, you're just like, oh yeah, that's like an easy differential equation, right? That's like stuff that, you know, an ODE person would just be like, oh yeah, I did that day 1 of my class. Or day 2 or something. All right. So that's the calculus fellows. Those are the calculus fellows. And again, they're kind of tied pretty closely into linear algebra here. So then we get into stuff. You know, I said Euclidean geometry is stuff that you use a lot. So basically, complex numbers. I mentioned those earlier, where they were the kind of 5 plus 3i thing. Well, basically, complex numbers, or rather the concept that you have sort of these extra specifiers so that numbers aren't just real values, they got more parts to them. Actually, non-Euclidean geometry and that sort of complex number concept come up again, like I said, I kind of alluded to the fact that they would in a way that you wouldn't expect. If you just want to do even really basic stuff in 3 dimensions, then obviously linear algebra will get you a lot of the way there. But as soon as you want to rotate something, if you ever want to do rotations, then you step out of the world of comfortable linear algebra and Euclidean geometry and into the world of non-Euclidean geometry, which you sometimes still use, well, often still use linear algebra to work with, but again, the Euclidean part falls away, and so you typically have to do a bunch of stuff related to that, but again, not on topic tonight. So basically, non-Euclidean geometry is geometry on surfaces that have nothing to do with those nice, pretty orthogonal ones that I drew before. They do not look like this, where you've got a nice XYZ. Instead, they are stuff like geometry on the surface of a sphere, for example. And so your coordinate systems might look something like that. And they have weird properties, like, for example, if I go the same distance along the different directions, I may not get back to the same place that I was on before. Like, you know, so I went this way and then that way, I might not get the same place as if I went this way and then that way, which is, you know, what one of the sort of hallmarks you might expect from Euclidean geometry. So you basically get a lot of interesting things that happen in non-Euclidean geometry, and you may ask, why do I care about that, and why does that have anything to do with rotations? Well, the reason is because rotations in 3D space just plain aren't Euclidean. The rules that they follow just kind of defy your logic a little bit in terms of what you would expect to have happen excuse me, with ordinary numbers. One of the examples is they do not commute properly. So for example, if I have a rotation where, you know, I'm going to spin something around one axis, and then I have another rotation of the same object that I want to apply where I'm going to rotate it around another axis, I can't flip the order of these two things. The orientation that the object ends up in after I do these two rotations, if I do A and then B, the orientation of the object will not be the same as if I did B and then A. Now, sometimes for certain rotations it will be, but for the vast majority of rotations it simply isn't. And so the attempt to represent these rotations has been a long and difficult battle in computer science and in mathematics in general. And there's lots of different ways in which these are attempt to be dealt with. They include the exponential map. They include Euler angles, right? They include quaternions. They include and duals of those, right? There's just a whole family of things. Rodriguez parameters, right? Or Euler parameters, which are not the same as Euler angles, et cetera, et cetera. Basically, there's a whole bunch of different things that people have come up with to try and represent these and work with them efficiently. And especially the most popular ones in use today, which are basically these guys, quaternions and their duals. Those are all about doing operations that are in non-Euclidean geometry space. A quaternion, for example, is four-dimensional, and it is in 4 dimensions but constrained to the surface of a 4-dimensional sphere, or hypersphere more specifically. And so if you think about that example I just gave where I said, this is a 3D sphere. I mean, it's actually 2D because I drew it in 2D. But imagine in 3 dimensions you have a sphere, a ball, and you've got essentially 2 parameters, right, that define the sphere. That would move you around the sphere, right? A sphere is a surface, so it's only got 2 degrees of freedom. From any point on the sphere, I could only really move in any two orthogonal directions at any given time, right? But another way to think about that sphere is, well, we could use 3 parameters to specify where we are on the sphere, right? And we could just say that the only possible sets of those 3 parameters that we're willing to consider are the ones that lie on the sphere. Because 3 parameters would allow us to specify anywhere in space. It could be out here or here or here, right? Anywhere in space, 3D will give us. But we just want this one sphere that's embedded in that 3D space. We could simply constrain our XYZs using some additional constraint, and I can tell you that that constraint happens to be basically that the length of that vector, right, equals some radius values. But that's a separate issue. So don't worry about that. Point being, we'd use a constraint to say that it has to fall on the surface of a sphere. Okay. The same thing could be done in 4 dimensions. We could say we have x, y, z, w. We have 4 parameters which would give us anywhere in 4D space, but we're going to constrain it to be on the surface of a 4-dimensional hypersphere, which gives us only 3 free parameters essentially, but that we're representing as 4. Now, if that doesn't make your mind explode, I don't know what does. Point being, those are the sorts of things that you have to work with. And believe me, after you start thinking about them, somehow they start to become second nature, even though they are incredibly complicated and involve weird stuff like trying to visualize 4 dimensions, which no human can really do adequately because we live in only 3. But not only do quaternions involve that, they also involve our old friend complex numbers, because not only do they consider having 2 parts, they actually consider having all 4 parts, and their arithmetic is defined in terms of those parts. So a quaternion will often be written in something that looks like, a plus bi plus cj plus dk, where I, j, and k are all sort of things that resemble this kind of I. They all have rules such as any 2 of them multiplied together equal -1 and these sorts of things. And so quaternions themselves would be very familiar to anyone who worked with complex numbers. They're sort of an extended version of that. And again, stuff that kind of makes your head explode a little bit if you're not used to math, but is absolutely commonplace in game programming. Make no mistake about it. So yes, non-Euclidean geometry and complex number sorts of stuff come up again, surprisingly often. If you're doing any 3D programming at all, you will basically butt heads with them almost immediately. All right, so beyond that, we've got sort of a bunch of other guys who I'll just mention. I don't want to spend too much time on them because, again, like I've only got, I got 12 minutes left. Okay. So what else we got in the grab bag of things? And again, these are all things I've personally had to implement at some point or another. I'm only doing maths in games that I actually had to use myself. And I still got about 7 more things here to list. Okay, so topology. Topology, I mentioned on the stream, actually, already. Topology is the study. You know what? I'm going to go ahead and I'm going to give myself some fresh room here because these things aren't as related anymore. Topology. I already mentioned on the stream, basically topology is the study of manifolds and how they are connected and this sort of stuff. Now, what's a manifold? Well, basically, if I have some kind of a space, we've already talked about one, that sphere, for example, would be an example of a manifold. Basically, if I have some kind of a space, so like before we said, let's say we have a 3D space. So we have basically an x, a y, and a z vector in our vectors, and we can specify our positions. Let me write that vertically. I want to get used to writing them vertically again because, we're going to be doing some mathy stuff. Anyway, so if I've got points in 3-dimensional space, they could be anywhere. If I start to talk about some subset of the entire space, that basically forms some kind of a shape, like a sphere, but it could be anything else, like some kind of a weird strip, like a road that's been laid down or something like this, right? Like maybe I've got my 3D terrain and I've got, here's my trees or whatever, and then there's a road that goes through it. Maybe I want to talk about that road as a surface. That's an example of a manifold. A manifold is something that is some lower dimensional space, in this case a two-dimensional space, right? It's a flat surface, 2D, that's embedded inside of a three-dimensional space. So it's in 3D, but it's only 2 dimensions worth of information, right? That's an example of a manifold. And topology is basically the study of these things, how they are connected, how they can be represented, and sort of things that you might need to know about them. So for example, on the stream, we already talked about the concept of toroidal versus disk topology. I said basically if you have a world where if I go off one edge, I come back on the other, if my guy can wrap around, that's an example of toroidal topology because it's as if you were on the surface of a torus, right? Of a donut, basically, like an inner tube, because you can keep going around in either of the 2 major directions and you just kind of loop around the thing, right? Imagine an ant walking on an inner tube. You get that exact same thing where it can just walk around and around and around in one direction and never seem to stop. And until it realizes it's just walking in circles, it doesn't realize it because it just thinks it was always going forward. Again, toroidal topology versus disk topology would be if you could get to the end. Disk topology would basically be I start walking and I get to a barrier that I can't go past anymore. And so we decided already, we basically already did a topological decision in our game. We decided to have toroidal topology instead of disk topology. Just something to think about. That's topology, right? And there's a lot of stuff to talk about in topology. Some of it comes up in games, some of it not so often, but it's a pretty wide field certainly. So moving on from there, Minkowski Algebra, which is not really a field of mathematics, I wouldn't say. It's just a thing that comes up a lot because of GJK. GJK is, well, not just GJK, but collision. Let me just say more broadly, because it's not just GJK, really. It's basically collision detection. And we may even use it in the collision detection in Handmade Hero. Basically, Minkowski Algebra is the algebra of shapes. It basically does things like if I have a square and a circle, I can add them together and get a rounded rectangle. That's the world's worst rounded rectangle. And basically I do that by tracing out the circle at each of the 4 corners of the square, for example, and then taking that sort of entire space that was formed by them, right? Typically this is used in games. It was used actually at least as early as Quake, possibly before then. I don't know what the earliest example of Minkowski's algebra in games is. And 2 typical uses of it. One is the GJK algorithm, which I will not explain here, but that uses Minkowski algebra at its core to do collision detection between moving convex solids. And so that's one example that's very common, but another example is just simple world shrinkage and growing. And what that basically is if I have a world, let's say this box here, and I've got a dude in the world who has, say, a spherical or cylindrical or something collision representation, I can choose to do my collision checking always based on trying to intersect circles with these line segments that define my boundary or something like this. But there's another option, which is to simply shrink the world in such a way that it now approximates what the sphere could actually go if the sphere was shrunk down to a point. So you're basically taking the world and growing it by the sphere and shrinking the player down to the point. And the collision that happens when a point moves around a sphere expanded world is the same as a sphere moving around the non-expanded world. So basically this allows you to do simple point operations or line operations for movement against world geometry without ever having to deal with the fact that things were actually spheres or cylinders in their collision representations. And again, I believe Quake used that in its collision detector. So that's Minkowski algebra. It does come up a lot in collision detection. Obviously, control theory, very popular. Control theory is basically, the study of things like feedback systems and springs and these sorts of things. There's things like the proportional PDCs, proportional derivative controllers, these sorts of things. Used a lot in robotics, basically. And we use it in games a lot to control variables that we want to control over time. So for example, if we want to do motion stuff, where we have something that we want to kind of like sort of pick up some speed and then slow down again. We might use control theory to kind of do that. If we have stuff like a missile that's chasing a target and it's supposed to turn at a slow kind of rate, again, control theory. It's basically all the sorts of stuff you might do in the real world to control real world robotics, weaponry, these sorts of things that we want to do in games to simulate the motion of things as they might move in the real world. And that's very common. Again, we'll be doing that in Handmade Hero a bunch. Proportional derivative controls will probably make an appearance. Other sorts of things like that. Definitely very popular. Okay, interval arithmetic. What is that? A lot of people probably have never heard of that. Interval arithmetic is basically a arithmetic on ranges. Just exactly what it sounds like. Basically what happens is sometimes you need to compute things over spatial areas, and that's where this really comes in handy. I don't know that that's necessarily what it was originally designed for. I don't think it was. I think it might have been originally designed for automatic differentiation or something like this, but point being, I've used it a bunch for area computations. What it allows you to do is it allows you to evaluate equations on entire ranges of values instead of just one value at a time. So you have some equation, x squared plus 5x or something like this that you want to evaluate, and instead of evaluating it for just x, you want to evaluate it for all the numbers between a and b, all of them. So if this was 3 and this was 1700, you want to basically be able to call f of x and find out what this equation can take in terms of its output for all the values in between there and there, right? And that's what interval arithmetic allows you to do. Now, where do I use this? I use this when I'm trying to compute what functions will do over regions. So for example, if I have a grid system for my game and we're bucketing things up, let's say even in a tile map, and I have a particular tile in the tile map, I want to know what the maximum water level could be, and I have a function for the water level. I want to know what the maximum water level is in here. I can do interval arithmetic on it to figure out what that maximum would be. I'll get out the minimum and maximum for it in one fell swoop instead of having to do a bunch of point sampling to figure out where it is. Very powerful for that sort of region checking. I've used it a lot in the past. Really cool, pretty simple to learn, and very, very powerful in the right circumstances, certainly. Okay, we've got graph theory. Probably needs no explanation. Graph theory is basically the thing that allows you to do all your studies of pathing and graph traversal, stuff like this. Even simple stuff like pathfinding on grids is often broken down to graph theory problems where, we've got sort of these sorts of searches. And technically graph theory, and you might say operations research, it's hard to say what you want to call these things. I'm not, again, not a mathematician, and I'm not a pedant on these things, so what each algorithm actually falls into in terms of discipline, I may never quite get right. I might say it's graph theory, but really that's technically an operations research problem, but operations research is kind of an umbrella term. I feel like graph theory is in there. I mean, I don't even know. So, if you really want to know, try to go dig up a good math, like maybe Mathematica or that online, what's that thing, Math World. There's that thing that Wolfram bought that was basically a giant compendium of mathy things. Anyway, so if you've got things like I've got some series of spatial things and I want to do pathing between them, find out how I can get from one to the other. I want to do stuff like figure out, what the widest span is or something like this on a level, on a connected set of levels or even tiles, that sort of thing. Just searches and understanding things about layouts like that. That's all graph theory in there. And studies of graph sorts of things. So pathing is the typical example that you'll often see, but there's a bunch of other stuff that you might want to do in there. Oh man, okay, still got a couple more to do and only 1 minute left. Might go a little bit long. But anyway, operations research, which I wrote down briefly, but I'll write down again because then we've got sort of another thing in there. Operations research I use a lot now. Basically, the umbrella term for figuring out how you're going to optimize things. So you'll see things like the Metropolis algorithm, right, which is a pretty powerful one. It's kind of the be-all and end-all algorithm when you're like, I just don't know how to solve this problem. Usually that means you solve it this way with the Metropolis algorithm, right? Basically what operations research is they deal with minimizing or maximizing something, right? So basically you have some criteria, and this is why it overlaps with the pathing again. If you want to find the shortest route between two things, that would be operations research. If you want to figure out the optimal distribution of some quantity among different parties based on some weights or that sort of thing, you get that again. You want to do something like figure out the most optimal ordering for a set of assembly language instructions. This guy right here, I've actually done that before. You get operations research anytime you want to try to maximize or minimize some criteria given a set of rules that you can use to structure something. And it's very, very general, right? You get a lot of stuff that can happen in there. Okay, so very quickly, I'll just throw out the last couple here since we're out of time. Probability and statistics, obviously, is something that we'll be using because we'll be picking random numbers and trying to do stuff where we determine what's the probability that the player will get a certain thing, and we want to control that in our level design. So obviously probability and stats probably don't need much introduction of where they're useful. You use them all the time, even in very simple ways, that sort of stuff, if you want to control distributions and other things like this. And then there's also, of course, all the discrete math topics, which I don't really know very much about. You typically leave them to the experts, but you have probability and pseudo-random number generators, right? Obviously, those sorts of things all involve the study of numbers at a very deep level, and they're the sort of basis for all that stuff. So any cryptography that you do, anytime you generate random numbers, you're all leaning on all the stuff that people have done sort of in that field. Okay, and so I'm trying to think if there's anything I forgot. We're right on time, so I'm hoping that I didn't, of stuff that I've done. Now, these are only the things that I could remember, so it's possibly that I had to do some things that I just didn't remember, but I believe that I got all of the major ones there. Okay. All right. So hopefully that is a final sort of place I can point people now that's like, if you have an hour and you want to know what kinds of math you should know if you're going to be a serious game programmer, that's the stuff that I had to learn. I don't really regret any of it. I feel like all of the math that I've learned in all of those disciplines was all pretty darn cool, and it's allowed me to always approach things with sort of a lot more weaponry than I would have had if I'd had to just kind of muddle through it as a programmer, and I think a lot of the solutions that I come up with would have been worse. And so that's what I can say about that. And so starting tomorrow, we will start learning about vectors and start programming with them so you can see how they work. And that will be the first thing that we'll start off with. And that, of course, is linear algebra, and geometry and trigonometry is right in that wheelhouse. That's what we'll be starting with. Whether we get to any of these other ones in the course of Handmade Hero will largely be dependent on what we need to do, but I can guarantee you we will probably hit at least 4 or 5 of them, if not all of them, in the course of the game somewhere. That is how common a lot of these things are if you want to do stuff right and actually kind of know what you're doing instead of just hacking it and crossing your fingers that it works. So yeah, so there you go. Let's open it up to questions. Please put Q colon in front of your question so that I will be able to see it. And please try to keep it to stuff we've done on today's stream or on a previous stream. In fact, today's stream, it might be good to kind of restrict it mostly to math questions tonight since that's all we've done today. But, you know, we'll see how it goes. All right. Let's see. I got to give you guys a chance to catch up here. Let's see. Do you even breathe, bro? Not much, no. I mean, I probably should breathe more. It's true. You said that toroidal topology means that if you walk in one direction, you'll eventually get back to where you started. Doesn't a sphere also have this property? How do we know our world is a torus and not a sphere? That is a fantastic, fantastic question. So let's take a look, actually. The answer to your question has to do with how we have unwrapped it, and you can kind of see, for lack of a better way of saying it, you can kind of see with how the motion on the torus works versus how the motion on the sphere works. So if you think about a sphere, and I wish maybe I should eventually install some kind of a 3D package on this so we can look at 3D things a little bit easier, because my drawings are not going to be very good, unfortunately. But if you take a look at what happens on a sphere, right? We have an XY coordinate system in our game, right? we were moving in xy coordinates. And what we were doing in xy coordinates is we were saying that we essentially have a tile map, right? You remember us constructing this tile map, and that tile map was the same everywhere, right? So, we have a y that goes up, we have an x that goes over, and we basically have this sort of grid that where things are always square, right? There's always a square, and no matter how far you go in any direction, even if you wrap all the way around, you're going to see exactly this kind of thing around you locally, right? Well, if you think about what would happen on a sphere, right? Imagine that we started kind of we're on the Earth and we start along the equator somewhere, and when we're right on that equator, right, things actually do look kind of like that, right? They do look kind of like they would here. But ask yourself, if I was to take that equatorial line and divide it up amongst the tile maps, how many tiles would I have around the equator, right? Now remember, as we go upward, we're still retaining that two-dimensional coordinate system. So we're still talking essentially about lat-long lines like they would be on the Earth. And if you know what happens if you ever looked at a globe, basically the space, the size of the rings of those lat-long lines continues to diminish as you go upwards. So if I had, I don't know how many tiles you want to consider, if I had 32 tiles around the equator before I wrapped around, by the time I got up here, I would be down to something like 4 tiles, and then when I got up to the very pole, I'd just have like one vanishingly small tile, right? So the reason that we are a toroidal topology and not a sphere topology is because we enforce the fact that the dimension of our tile map does not diminish in any direction. We always have the same number of tiles, width and height-wise, right? No matter where you are. The width of our tile map in terms of tiles, the count of tiles along the y-axis, does not depend on the x-axis location, and vice versa. On a sphere, that would not be true. On a sphere, we would have to basically modify how many tiles there were as we went upward, or modify the size of those tiles, right? Furthermore, when you actually got up to this point, all of these tile lines would actually vanish into a single point, right? And at that single point where they vanished, you would no longer know even which tile you were on. So when you went to wrap around to the other side of the world, you could essentially, the player would be free to almost choose to be on any of the tile paths when they got up there, right? If we didn't shrink down. Does that make sense? So basically there's two choices, right? We could either shrink the number of tiles or keep the tiles number the same, but have them all diminish in size till they got to a singularity point. And that's what happens at the top of that sphere. So topologically speaking, we basically have no options on a sphere for actually preserving that coordinate system that we wanted without making some very significant sacrifices. By contrast, on a torus, right? Don't know if I can draw one here. By contrast, on a torus, these lines never converge, right? Basically, the ring around here, right, and the ring around here, they never get closer together. They never... The spacing between these is always equidistant the whole way around the torus, right? So we can always lay down a grid, and that grid never gets wider or smaller no matter where we are on the torus, right? And that's why, that's why that is the way it is. Oh dear. Well, we have a bit of a problem, ladies and gentlemen. The laptop has run out of batteries, but unfortunately, it's the laptop that has the questions on it. Oh boy. Well, that is unfortunate. I guess we will have to pause the stream for a minute here at 9:10. Pause for 1 second while I get a battery of some kind. Oh no. Okay, that was unfortunate. Lesson learned. It's true, my laptop cannot go. Let's see here. How horrible. Well, lesson learned. I guess I'm going to have to get a spare, but like this laptop basically can't last hardly at all. It dies immediately, basically. I do not know why. I have no idea why. I don't know if it's just that the battery's old. And of course, Linux always reports that it has like half the battery left or something, and then it dies. So it's like you don't even get really any warning that the laptop is about to die. It just goes away. So unfortunately, I will have to restart. Okay. All right. The laptop is back now, thankfully. And so let's see. Let's get HexChat open here. HexChat. There we go. So at least we can see the questions again. And now, all right. So please, if you had a question, obviously I didn't catch it because the laptop died. So please repost your question with a Q colon, and I will re-pick up where we left off now that I can actually see questions again. Yeah. Fantastic. Gotta get a power brick for this room, so it'll always just be plugged in if it's in here. Yeah. Do you think it's important to clarify that many of these subjects are things you can learn as you need them, and it's more of an overview of math, of what math is used in games, not what is needed as a baseline? Yes. Well, I mean, hopefully I said that relatively clearly when I said it's stuff that I learned as I went, but yeah, you don't need to learn it to start game programming at all. But of course, as you've seen on Handmade Hero, you've been able to probably follow most of the stuff that I did and hadn't had to do that. So you'll see as we go forward in programming exactly when each thing kicks in. And it's like, that's the time that you would want to learn it. In terms of if you are starting game programming, though, I highly recommend learning as much math as you can as you go. Basically, like, you know, just constantly be studying in the background if you can be until you know a fair bit of math, because there's really a ton of it. And like, I actually wish I knew more. There's a bunch of stuff I don't know. Like, I don't know geometric algebra, for example, and I wish I did. I only know like the barest little minimum of it. There's a bunch of things that I wish I knew. So. I think you were confused about non-Euclidean geometry. The space of most 3D games is Euclidean. Well, that's what I said, if you remember. I said the 3D space of most games is Euclidean, but what I said is non-Euclidean geometry you have to use almost immediately, and the reason is because rotations are non-Euclidean. That is not me being confused, that's the truth. Basically, rotations, I shouldn't say rotations are non-Euclidean, the representation for rotations that we use in 3D graphics is non-Euclidean. Quaternions are non-Euclidean. Basically, they are the thing that you will see used most often to represent rotations. And so if you want to understand them, you have to understand non-Euclidean geometry because they are non-Euclidean. What happens in partial differential equations if if Scott Myers is in a gorilla suit and distracts you so much that Strausser in a green car can swap your briefcase full of compression-oriented code for OOP? I would basically say that it depends whether you are actually sitting there trying to bring the briefcase to your boss or whether you're observing it from a green car waiting at a red light out on the airport drive. Are you using a mouse or digital pen? I'm using a digital pen. Do you take a do you take a trail of Coke before you start the stream? No, I don't. I don't really take anything. Let's see. Don't the tiles near the inner part of the torus get smaller than the ones near the outside? So isn't the topography more of a magic cylinder in which each end is hooked into each other? Well, so not really. And the reason for that is just because, like I said, its topology often isn't about the actual size of things. It's about whether there could be the things, right? So try to explain this a little bit better. So basically, inside the torus here, topology is about how they're connected, not how big they are. So as long as they don't vanish like they do here, you're okay, right? The problem here is that it becomes invisibly small. It shrinks down to a single point. And that means that at this point, there is no longer any notion of the connectivity between the rows of the tiles and anything else, right? So you can't follow a line along here and expect to end up in the right, on the right tile thing when you get back to the other side, right? It's kind of hard to say exactly why that's the case there. So typically, like the problem with the sphere is basically that you have that singularity at the top where everything disappears into a point. Whereas the torus never has that. So yes, these would be smaller if we were talking about the actual geometry of a torus, but they never get any smaller than that, and they re-widen again out here. So they're always completely represented through the entire way. Yeah. You would have to ask an actual topologer for a better explanation than what I gave, because again, I am not a mathematician, so my explanations of things are largely based on my functional knowledge of how they work, and not necessarily a very good pure mathematical explanation. And so really, like, again, they would probably give you explanations that are more about what happens locally on the surface, and less about sort of the more intuitive explanation that I gave. But yeah. So if you did want, though, to represent it somehow magically perfectly, you are correct. A torus isn't quite right, because if you wanted to represent the spatial part correctly, you would need it to not get smaller on the inside, which is kind of impossible to do, right? Because it's going to be the ring is smaller here. Now, one of the dimensions is fine. The ring dimension that goes around is fine, because that's always the same size no matter where you are, but this one is smaller than this one in terms of the inner and outer. So yeah. How is dealing with complex numbers and 4 dimensions better or more useful for doing rotations as opposed to using a rotation around an arbitrary axis matrix? I don't get how quaternions are better. So there's a lot of ways that quaternions are better. And I will show you a simple example. So let's say that you want, and I'm not sure exactly, what you mean by the phrase using a rotation around an arbitrary axis matrix. So I don't know what you actually mean by that, but I'm going to assume that what you were referring to is a rotation matrix, right? So you were talking about an R matrix, which is basically a matrix, that looks something like, one of these kind of matrices. Sort of things, right? Well, actually, that's not quite right. We need an extra 1 in there. That's bad. So we're talking about a rotation matrix where we basically have like a cosine sort of sine sort of a thing. I don't actually remember exactly how this would look. It's like a negative sign here. One of these kinds of guys. You're talking about this sort of thing where you basically have something like this. A rotation matrix, and I guess arbitrary axis means it would be more complicated than this because that's a single axis rotation. So I don't know how to write one of those matrices out by hand. But yeah, so you're basically talking about a rotation matrix that's some 3-dimensional rotation about some axis. So we'll say that it's a rotation matrix that's parameterized by an axis and an angle. Is that basically what we're talking about here, hopefully? I don't know. But let's say that that's what you were talking about. So we have rotation matrix versus a quaternion that's going to basically be the same quaternion. So you're representing it the exact same rotation around some axis with a theta, right? So basically, the reason that you want to use quaternions instead of rotation matrices are, the very first one is efficiency. So one of these matrices is going to at least run you 3 by 3 or 9 values, right? So anytime you're computing with one of these, you essentially have to do a 3 by 3 matrix. So you have to store 9 values, and those 9 values have to be renormalized continuously, right? Because basically, one of the requirements for a rotation matrix in order for it to be a rotation is that it cannot change the size of anything, right? That's what makes it a rotation matrix, is that the size is invariant. So that basically means that all of the axes in it have to be orthonormal and blah blah blah. So you've got a matrix that's basically 3 vectors, and those vectors have to be unit length. Like this guy, and this guy all have to be unit length, which also implies that the rows are unit length, right? So basically, you've got this rotation axis. It's much less efficient to store because the quaternion only requires storing 4 values, right? So already we're kind of at an advantage if we're in quaternion space because we've got 4 values instead of 9, and that's kind of handy. Furthermore, when we actually do operations on these guys, there's a number of operations that we can do extremely trivially on the quaternions that actually are fairly expensive on a rotation. So for example, if I want to actually construct one of these guys, right, I have to take the sine and cosine and fill out all 9 values. This guy, I actually only have to fill out the 4 values and only have to take the cosine of the thing. Now that's actually kind of special because since I don't need the sine, right, you need the sine for the rotation matrix. Since I don't need the sine, I can often compute the cosine as a byproduct. The reason for that, and again, we're kind of getting off into la-la land here, but I'm just throwing out some examples for you since you asked. The cosine of theta can often be directly computed as the dot product between two things, right? So you never actually have to take a cosine, you never actually have to do a transcendental. Typically, like if you want to know the angle between two vectors, you just do A transpose B and you get the cosine, right? If these were normalized, you get the cosine for free. If not, you have to normalize that, but that's usually small potatoes between compared to doing a sine cos, which you'd have to do for this guy, right? So typically you can actually compute quaternions wholly without trigonometric functions altogether, which is kind of amazing. Whereas for rotation matrices, you're never getting away with that. You got to do at least that and possibly more depending on, if you're doing Rodriguez formulation where you're doing the full rotate around an arbitrary matrix. You're talking about a lot of operations to initialize those 9x9s. And then furthermore, you got to do 3x3 matrix multiplication to compose them. So every time I want to combine one matrix with another, I got to do a full 3x3 times 3x3 operation to compose the matrices. And I don't have to do that with quaternions. Quaternions have a much simpler composition form. It's not quite as simple as just like, adding them together or something like that, but it's still pretty good, right? So you've got all that. But you've also got a bunch of other stuff that happen with quaternions that are much more powerful than matrices. Quaternions have this nice property that they actually represent things sort of over the space of double rotations, not single rotations. And I'm not going to try and explain what that means right now, but I will simply say that if you have 2 quaternions or more, you can oftentimes deal with them rather directly as if they were vectors and normalize after the fact, which is something you cannot do with matrices because they will degenerate quickly. So for example, let's say that I have several orientations in space. For example, I have 5 animations playing, right? I have 5 animations playing and I want to blend them all together at the same time. So I have 5 animations playing for a guy's run. It's like, maybe that's a little bit unrealistic. Let's say we have 3 animations playing. So I have 3 animations playing, and each of those animations is going to compute a position for the guy's head, his neck, right? So I've got his neck, and each of the 3 animations, well, one said it was pointing this way, one said it was pointing that way, and one said it's pointing this way, right? Now, because my animator wanted to do some tweaking and whatever, we've got blends between those animations. So we say that we want 30% of animation A plus 40% of animation B, which leaves, of course, 30% more for animation C. Okay, so that's the equation I want to compute with my orientations to figure out what the resulting orientation of all these guys should be for the neck of my character. Okay? Now, this is something you've done in our animation tools without even knowing it, right? You weight animations that you blend together. So we all know this operation. It's like I want to blend 3 animations together to get a resulting animation, okay? Well, if I want to do that with matrix math, you're almost dead in the water, actually. Because you don't know how far, like these 2 diametrically opposed animations are going to cause you some pretty severe numerical problems potentially, especially if they look like that. Because once you start adding 30% of one thing and 30% of another thing that happen to be diametrically opposed, you will start to collapse down to here. So you can't just add these matrices directly together or you'll get really bad degeneracy as you try to like blend these things together and you'll end up with almost all this animation, even though that's not what should have happened. Quaternions don't really suffer from this problem too much. Quaternions, because they represent a larger space of rotations, they actually represent twice the total space of representations. Don't ask me about that yet because we're nowhere near that. That's a topic that's probably beyond Handmade Hero, but that's what they do. Because of that, you can actually add these things together much more reliably because this situation almost can't happen. You basically get a case where even neck orientations that are very far from each other appear in quaternions to actually be much closer to each other than they are. Twice as close, in fact, as matrices, which means that if you add them together, you can actually directly add them together and normalize after the fact, and you will get much better behaved systems. And not only that, but instead of adding 9 numbers together each time you do one of these adds, and then having to renormalize the whole thing, which is basically renormalizing the entire matrix that's 9 numbers, you basically are just adding 4 numbers together. So it's just 4 plus 4 plus 4, and then you renormalize just those 4, right? Much, much cleaner. So easier to construct, smaller to store, easier to work with, much better numerically behaved, can also do stuff like neighborhooding. There's a ton of reasons why quaternions are better. So basically, like if you're using 3x3 matrices to represent your animation data or your orientation data in 3D world, you're probably a sad panda. What can I say? Ever do anything with Laplace transforms? Not personally, but what's going on here? Did I just lose my stream? Are we still live? Why did it say reconnecting? I don't know. Looks good. I'm going to assume I'm still alive. Ever do anything with Laplace transforms? Not personally, but if I remember correctly, spherical harmonics, Laplace. Don't you use them in spherical harmonics? I don't actually know. I feel like the Laplace transform is used in spherical harmonics a lot. I could be wrong about that. So I don't use them. I'm not much of a rendering guy. I don't do a lot of rendering code. I feel like Laplace transforms happen these days, though. That's what I feel like. But I don't actually know. So that's, yeah, I'm not sure about that. What type of math is used in AI, specifically prediction and reaction of to player choice? I'm not an AI expert, so I don't really know what kind of math they typically use. I don't know, maybe Bayesian networks and that sort of stuff. You know, I'm not sure. Certainly optimization, like operations research, is an AI kinds of thing. So you use a bunch of that, I'm sure, but I don't know. I'm not really an AI expert, so I'm not sure to say. Is all of the things shown in math classes useful? Sometimes stuff seems so unnecessary and mind-killing. What's your opinion on that? My opinion is yes, it's probably all useful, but it's all taught very poorly. So my assumption is that almost everything that you actually see in a high school math class is actually particularly useful. However, you would never know it by the way they teach it, because they typically teach it in a way that it will be almost impossible for you to even think of how it might be used. And only later in life, when you actually find places where you start using it, you go, oh, that's why I would need to know that. Let's see. Okay, quaternions, as you use them in rotation, are definitely not Euclidean. They're not. Like, they just aren't. You cannot treat them Euclideanly because they have a normalization constraint to them, right? And so basically, when you're doing quaternions, I don't really want to argue with people on stream. Quaternions, as you use them in rotations, are not Euclidean, period. We'll just end it there. Can we talk a bit about what out of the master list we expect to use in this game? Yes, so we'll use arithmetic, algebra, geometry, trigonometry, calculus, obviously. I don't know whether we'll use partial differential equations or ordinary differential equations. We'll definitely use linear algebra. Euclidean geometry we'll definitely use. I don't know if we'll ever use any non-Euclidean geometry because we're not doing 3D. Topology we already mentioned even on the stream. Minkowski algebra we'll probably use in the collision detector. I don't know whether we'll use any numerical analysis, which is like iterative methods for solving things, but possibly. Control theory, definitely. Interval arithmetic, possibly, but I'm not sure. Discrete math, obviously, but I don't know it very well, so we'll probably just be using mostly what other people have done. Like, we'll go use someone's pseudo-random number generator, and we won't necessarily talk about how you construct it because I don't really know how to construct a good random number generator. Graph theory, almost definitely. Probability and statistics, almost definitely. So yeah. Will the next few weeks cover the basic functionalities that are math heavy, or will you spread it out the topics more? Yeah, we'll basically be covering them when we get to them. But now is the time when I have to start talking about math because there's really nothing left to do in terms of our engine work that isn't going to be using at least vectors. So that's why I decided to kind of have this stream at this point in time. Let's see. It's nice to see you recommend learning math so strongly. Did you learn most of it from books or did you take courses? All books, really. I've never taken a math course since I got out of high school. I heard Markov chains are also useful crossing control theory with probability. Will we use these? I don't know. I mean, it depends on how we implement our world generation. That's probably the only place that we'd really have a chance to use them. Obviously, I mentioned the Metropolis algorithm, and I feel like that's technically filed under a Monte Carlo Markov chain model. I don't really remember, though. And so, you know, if we use some kind of permutation-based world generator, maybe a Markov chain is technically involved there. I'm not sure. The internet pedant police doesn't forgive oversimplifications. Why do you even bother? It's a good question, but the answer is because it's my stream, and that is kind of nice because it means that what I say goes. So I try to be pretty nice to people who write in, but if someone wants to argue about a math thing, I just don't care because at some level it's like I only know the math that I know, and I can only explain things that I know. And so I already said at the very beginning of the stream, if you really want to know the very specific math terms for everything, you will have to look them up yourselves. Because not only do I not know them, but I don't think I could ever know them all. I know a lot more math that I use day to day than I could ever possibly really remember all the specifics for and still be a very productive programmer, right? Like the level of specificity you need to always say the exact right thing in terms of a math explanation is way beyond what I think anyone who does as much different types of math as I do could do, unless you were just some kind of like an idiot savant or whatever, right? So it's gonna happen, get used to it, and I'm more than happy to have people post corrections on the forums for people who want to know specific math terms, or like, he said that this was X here, but it was actually Y or whatever in terms of like, you know, this term or that term. So if people want to learn the actual terms, that they'll have links. Let's see. So the people are saying that the stream dropped out. Yeah, it definitely said reconnecting on my side, but for some reason it still says drop frame 0, which means I feel like this counter is not particularly accurate. That's kind of frustrating because it means I have no way of knowing that what happened, which is kind of annoying. But I saw the reconnection dialog, so I know it went down, but I don't know why it didn't tell me. OBS. Let's see here. All right, looks like we're basically done. So that is the end of the stream. Thank you everyone for joining me for a little math. I can't say it has been a pleasure programming with you because we did not program, but it has been a pleasure going over math, of course, which is very useful in programming, and which we will be making increasingly frequent use of as the stream goes forward. So I hope you will not be shy about exploring math on your own and kind of looking into the math topics that we cover, because there are a lot of really important math things out there to learn, and it does take a little bit of dedication on everyone's part to kind of go learn the math that they don't know in time to do stuff in Handmade Hero. So thank you very much for joining me. If you would like to follow along with the source code starting tomorrow with the math and so on, if you want to pre-order the game, you can go to handmadehero.org, and if you pre-order the game, it comes with all the source code, so you can basically download it every night and follow along with what I do on the stream. If you want to support the video series, we do have a Patreon you could subscribe to. And if you'd like to learn along with the series, we do have a news and forum site. That is where I was saying people could post corrections to math statements I make in this code discussion forum, for example. It also has an episode guide. It has a schedule for the week posted as well. It has an episode guide that you can use to catch up on past episodes that you missed. And it's got a coding resources page with ports to Linux and Mac and stuff like that you can use if you're trying to run Handmade Hero on another platform from the source code. So hopefully you will check that out if you're interested. Thank you very much for joining me. I will be back tomorrow at 8 p.m. Pacific Standard Time to talk a little bit about vectors and do some code with vectors with you so you can start to see how they work in the real world. So thank you everyone for joining me, and I hope to see you tomorrow.